Hi, I'm Scott Nakui. In this video, we're going to look at the inverse displacement solution for spatial manipulators. So by the end of this video, you should be able to understand some of the challenges of solving inverse displacement problems for spatial manipulators. As well, you should be able to classify the workspaces of a manipulator. So the inverse displacement problem is, what are the joint variables required to achieve a given pose? All right, and by pose we mean position and orientation of the end effector. So if we let the desired pose of our last frame of our robot, which is frame n, say, it's going to be given by the following. All right, we're going to describe frame n with respect to frame 0. It's going to have an orientation component represented by the rotation matrix, and it's going to have a position vector. All right, and so we can write this out as this matrix here, and these would be known values. All right, because we're given the pose for this problem. These would be known values, i.e., these are numbers. Okay, so you'd be given that. Now, from the forward displacement solution, which we've looked at in prior videos, we know that we can find an expression that describes frame n with respect to frame 0 by multiplying each of our link transformations. So the link transform describing frame 1 with respect to frame 0, which is a function of our joint variable 1. Here we're assuming joint 1 is a revolute joint. All right, T2 with respect to 1, and then we're going to multiply them all up to the last transform that describes frame n with respect to n minus 1. Okay, and which is also a function of the joint variable. Again, here we're assuming a revolute joint, but it could also be a prismatic joint, and in that case it would be dn as our variable. So what we have is we have this matrix of our values, which is our known pose, and from this forward displacement solution we have a set of equations in terms of our joint variables. So we can equate these two. All right, so let's do that. So we're going to equate our forward displacement solution to our desired pose. All right, and so that's going to equal nx, ny, nz, ox, oy, oz, ax, ay, az, and our position px, py, and pz. All right, so we're going to call this equation star. All right, so the left-hand side are expressions in terms of our joint variables, and our right-hand side are known values. So we can make some observations about this equation, or sets of equations actually, denoted by the star here. So equation star is essentially 6 independent equations. So if we go back to our equation here, all right, you can see we actually have 12 variables here, or 12 numbers I should say, nx, ny, and z, ox, oy, oz, ax, ay, az, and px, py, pz. All right, so there would be 12 equations, right, one for each of these terms based on our left-hand side here. But we need to keep in mind that there's actually only 6 independent equations, because this rotation matrix part here, all right, although it's 9 equations there, it's actually just 3 independent equations. We have 3 variables that can represent pose. We saw that when we looked at, say, fixed angles or Euler angles. We only needed 3 parameters, alpha, beta, and gamma, to represent the pose. All right, so these 9 equations actually are in essence 3 equations, 3 independent equations, I should say, and then we have 3 independent equations associated with the position. So although we have 12 equations, in essence, there's only 6 independent equations. Now, the challenge is these equations are, in general, nonlinear equations. All right, so we have a lot of cosines and sine terms, and this results in the equations being nonlinear, so they can be difficult to solve. All right, and because of this nonlinearity, or the nonlinear nature of the equations, all right, depending on the number of joint variables and the robot's structure, so how the actual links are related to each other, our inverse displacement problem may actually have 0 solutions. It could have 1 solution, or it can even have multiple solutions. All right, and we saw this when we did the inverse displacement for the planar case. We showed that there's 2 solutions for that planar simple 3R manipulator. All right, sometimes we'd only have 1. Other times we'd have 0 solutions. That means it's outside the workspace of the robot. We can't actually get to that. You've specified a pose that the robot just simply can't reach. Okay, so this poses some challenges in order to solve our inverse displacement problem. So the idea of workspace of a robot is related to whether a solution exists or not. Okay, and so we define 2 workspaces. There's the reachable workspace, which is the region that the robot can reach with at least 1 orientation of the end effector. Okay, so it could maybe only 1 certain orientation it can get to that position, but that would be part of the reachable workspace. And then we have the dexterous workspace, which is the region where the robot can reach with all orientations of the end effector. So let's look at an example of each of these workspaces. Okay, so for our example, we're going to just do a simple planar case to illustrate the concepts. So we're going to have a 2-link robot. All right, it's going to have 2 link lengths, L1 and L2. All right, it's got 2 joints, so we have joint 1 here. We have joint 2 here. Okay, and this would be a 2 degree of freedom. It's an RR planar robot. All right, let's look at 2 cases. In the first case, we're going to have L1 is equal to L2. So in this case, our reachable workspace is simply just going to be a disk of radius 2L1, all right, centered at joint 1. So we can reach, imagine these stretched straight out. We can reach any point in that stretched out area. Okay. So that's fairly straightforward what the reachable workspace would be. Now let's look at what the dexterous workspace would be. And now remember, the definition of dexterous workspace would be any position where we can achieve any orientation of the end effector. All right. And for this case, our dexterous workspace is actually only a single point. All right. So it's only 1 point. And that point is at joint 1. All right, so we could draw a simple picture of this. We have link 1, there's joint 2, and then when the arm, because L1 equals L2, when the arm is folded back on itself, that point is our dexterous workspace. All right, because we could rotate around joint 1 here, so we can achieve any orientation of the end effector at that point. But as soon as you go to any other point, we can't achieve any orientation of the end effector. So that's an example of reachable versus dexterous workspace. Let's look at one other case here. Case 2, we have L1 greater than L2. The reachable workspace in this case, right, is simply going to be the region of outer radius L1 plus L2 and inner radius L1 minus L2. Okay, so we can draw this. There's L1. There's L2. Oops. So we're going to have this outer donut. It's basically a donut. And then the inner would be, if we were to fold L2 back here. These aren't very good circles, but you get the idea. This hashed area would be the reachable workspace. Okay. So when we fold that link back on itself, we can reach the points along this inner, and then any point in between the inner and outer circles there. And the question is, well, what is the dexterous workspace? For this case of L1 greater than L2? Well, it actually doesn't exist. There is no dexterous workspace. So it does not exist. All right, because we saw for the previous one, our dexterous workspace was when L1 equaled L2 was just that single point at the center at joint 1 here. Well, in this case, we can't even reach that point. So we know there is no dexterous workspace for that example. All right, so this relates to solution existence. So when we're doing our inverse displacement, all right, if I say I want to get to the position and orientation outside here for this case, well, I can't reach it. So no solution would exist. Likewise, if I command a position and orientation in here, I couldn't reach it as well. Okay, so workspace plays a role in terms of solution existence. Now, another issue that arises is that we could have multiple solutions. Okay, and we saw that for the planar 3R robot. So let's do that as our example again, and we'll just illustrate that here. So we have the 3 degree of freedom, RRR, planar robot. Okay, and so in this case, we could use our third joint of our robot to get the desired orientation we want. So it can be used to achieve the correct orientation of our end effector. Okay, so we can draw that. So here's, say, our desired position, and our desired orientation could be in this direction. Draw that a little straighter. Okay, so that could be our desired position and orientation of the end effector. Well, if we were to draw our base pin, and we now have links 1 and link 2 to deal with, well, we could have link 1 go this way and link 2 go that way. So that would be one solution. So we'll call that solution 1. But clearly, you should be able to see that we could have another solution like that. And that would be solution 2. And both are viable or valid solutions. Okay, so clearly, two solutions exist for theta 1 and theta 2. So whatever you choose theta 1 will obviously result in a different theta 2. All right, and so this poses a challenge as well when we do our inverse displacement solution, because we need to be able to find all viable solutions. All right, and so this ideas of solution existence, whether based on the workspace, as well as this thing of multiple solutions due to the nature of our robots and the nonlinear nature of our equations, these poses a lot of challenges to solve these inverse displacement problems. So in our next few videos, we're going to do some examples of solving inverse displacement solutions for spatial robot arms. And you're going to see some sort of tricks and tips we can do to solve these nonlinear equations in order to find a closed form analytical solution. Now, some layouts, there are no analytical solutions. You'd have to use a numerical method to solve it. But we're going to focus on layouts where we can find an analytical solution. So you'll see that in the upcoming videos.